A simple electrical circuit and the standard schematic representation of a battery conducting path under load. Schematics are very useful in visualizing the main features of a circuit. A single schematic can represent a wide variety of situations. Hi everyone, welcome to the new session of Electric Current Part 2. This is MK Chakravarti. So before going to the topic, we recall the previous knowledge of this lesson. In the previous chapters, we learned that electric current is defined as the amount of charge crossing any cross-section of the conductor in 1 second. It is denoted with the letter I. Its SI unit is ampere. So we also learned that when the ends of the conductor are connected to the terminals of a battery, a uniform electric field is set up throughout the conductor. This field makes the electrons move in a specified direction. So what are the learning objectives of this lesson today? Student able to draw schematic diagrams of simple electric circuit. He describes the direction of charge flow in conventional current. He defined drift velocity and he used to drift velocity and its formula to calculate current and vice versa. So this diagram shows a truck battery connected to a headlight. We know that the lighting the street in front of the truck. Here a simple circuit is shown. So this is called a simple electric circuit schematic diagram. Such schematics are useful because the analysis is the same for a wide variety of situations. Need to understand a few schematics to apply the concepts and analysis to many more situations. Again, come back to the schematic diagram of simple electric circuit. It is a closed path for current to flow through is supplied by conducting wires connecting a load to the terminals of a battery. In the schematic, the battery is represented by the two parallel red lines. Conducting wires are shown as straight lines, and the zigzag represents the load. The schematic represents a wide variety of similar situations. The second animated diagram will show the actual direction of the current. Look at that current. It goes from positive terminal of the battery to the negative terminal of the battery. The main objective of this lesson is what is the actual direction of the current. Look at the diagram. The conventional direction of current is taken to be the direction of flow of positive charge, that is, in the direction of electric field, and is opposite to the direction of flow of negative charge as shown in figure. Observe the diagram carefully. You will understand that current I is the rate at which charge moves through an area, such as the cross section of a wire. Conventional current is defined to move in the direction of the electric field. In the first diagram A, it shows that positive charges move in the direction of the electric field and the same direction as conventional current. In the second diagram will represents negative charges move in the direction opposite to the electric field. Note that conventional current is the direction opposite to the movement of negative charges. The flow of electrons is sometimes referred to as an electronic flow. Here also, you note that the direction of current flow in figure is from positive to negative. The direction of conventional current is the direction that positive charge would flow. Depending on the situation, positive charges, negative charges or both may move in metal wires. For example, take a metal wire, current is carried by electrons. That is, negative charges move. But while you take salt water, KCl solution, copper sulfate aqueous solution, these are the ionic solutions. In such ionic solutions, both positive and negative charges move. This is also true in nerve cells. Before going to the next learning objective, drift velocity of free charges, we had to know some facts about electricity. Electric signals are known to move very rapidly. We know that telephone conversations carried by currents in wires cover large distances without noticeable delays. Similarly, most electrical signals carried by currents travel at speeds on the order of 10 power 8 meter by second. It is a significant fraction of the speed of light. We know that the speed of light is 3 into 10 power 8 meter by second. But interestingly, the flow of current is denoted as the flow of electrons. But the individual charges that makes up the current move much more slowly on average, typically drifting at speeds on the order of 10 power minus 4 meter by second. How it is possible? Let's move to the next topic. By the conversation, we will know that the question arises is, how do we reconcile these two speeds? One is going, the electricity signal is going with the order of 10 power 8 meter by second in the light speed, but individual charges are moving with the speed of 10 power minus 4 meter by second. How do we reconcile these two speeds, and what does it tell us about standard conductors? Look at this diagram. When the charged particles are forced into this volume of conductor, an equal number are quickly forced to leave. The repulsion between like charges make it difficult to increase the number of charges in a volume. The charges enters and the charges leaves almost immediately, carrying the signal rapidly forward. But again, go back to the previous knowledge. When the ends of the conductor are connected to the terminals of a battery, the uniform electric field makes the electrons move in the specified direction. So the questions are, in which direction do the electrons move? Do the electrons accelerate continuously? Do they move with the constant speed? These questions should be answerable. Again, come back to the fact that the individual charges that make up the current move much more slowly on average, typically drifting at speeds on the order of 10 power minus 4 meter by second. Actually, what is the drift velocity of electrons? How can we consider this concept? Look at this diagram carefully. We assume that a metallic solid consists of atoms arranged in a regular fashion. Each atom usually contributes free electrons, also called conduction of electrons. These electrons are free to move in the metal in random manner. Almost the same way as atoms or molecules of a gas move about freely in a container. It is for this reason that sometimes conduction electrons are referred to as electron gas. Here you note that the average speed of conduction electrons is about 10 power 6 meter by second. It is also a fraction of light speed. We know that no current flows through a conductor in the absence of electric field. Because the average velocity of free electrons is 0, on an average, a number of electrons moving in plus x direction is same as the number of electrons moving in minus x direction. That means there is no net force of charges in any direction. The conduction electrons are frequently collide with the atoms of the solid. So what is meant by drift velocity actually? How can we define it? Look at the diagram. The drift velocity is the average velocity of the free charges. Drift velocity is quite small since there are so many free charges. If we have an estimate of the density of free electrons in a conductor, we can calculate the drift velocity for a given current. The larger the density, the lower the velocity required for a given current. And look at this diagram. You observe that take one free electron. These free electrons moving in a conductor make many more collisions with other electrons and atoms. The path of one electron is shown. This path of one electron is opposite to the electric field produced in the conductor. The average velocity of the free charges is called the drift velocity. It is denoted by the V suffix d. And it is the direction opposite to the electric field of electrons. The collisions normally transfer energy to the conductor, requiring a constant supply of energy to maintain a steady current. Look at this diagram. Observe the visual carefully. On applying the electric field, the conduction electrons get accelerated. The excess energy gained by the electrons is lost during collisions with the atoms. The atoms gain energy and vibrate more vigorously. The conductor gets heat up. Shows how the motion of electrons is modified when the electric field is applied to the conductor. Now let us obtain an expression for the drift velocity of conduction of electrons. Observe the figure carefully. We know that the drift velocity is the average velocity of the free charges. Look at the diagram carefully. Let the number of free charges per unit volume is given the symbol N, and it depends on the material. Here the shaded segment has a volume A times X. Here what is X? X is equal to Vd into time, that velocity into time. That means it is a distance that charge moves. Let the charge q is moving a certain distance x. That x value will be equal to Vd times t. So what is the volume of that part? The volume of that part is A times x, because we know that the formula of volume is area into length of the conductor. So A into x. So that the number of free charges in it is n into volume. The volume is Ax times n. The charge delta q in the segment is thus q times nax. Here note that q is the amount of charge on each carrier. For example, when you take electron, the value of q is taken as minus 1.60 into 10 power minus 19 coulombs. We know that current is charge moved per unit time. All the charges in the shaded volume of this conductor move out in a time t, having a drift velocity Vd is equal to x by t. Look at the figure carefully. If all the original charges move out of this segment in delta t, the current is given as I is equal to delta q by delta t. We know that by substituting values of delta q, we will get I is equal to q times NAX by delta t. Here note that x by delta t is the magnitude of the drift velocity, so it can be replaced by the letter Vd. Then we rearranging the terms, we will get the equation I is equal to nq a times Vd. Here I is the current through a wire of cross sectional area A made of a material with a free charge density n. In upcoming videos, we learned that how we can find the free charge of electron density n of a material. Let's continue to the topic. The carriers of the current each have charge q and move with a drift velocity of magnitude Vd. So we can conclude that the formula of the drift velocity is Vd is equal to I is equal to nqa. We will get that formula by rearranging the terms gives in the I is equal to nqa Vd. But in the previous topic, we mentioned that free electrons. What do you mean by free electrons? Look at the diagram carefully. In the second visual figure, we cannot see any free electrons, but in the first one, we are observing so many free electrons are there. Atoms in a metallic conductor are packed in the form of a lattice structure. Some electrons are far enough away from the atomic nuclei that they do not experience the attraction of the nuclei as much as the inner electrons do. These are the free electrons. The second visual shows these are the electrons in the insulator. Okay, we derived the expression for drift velocity of free charges, but by using the formula, we solve a particular problem regarding this item. Calculate the drift velocity of electrons in a copper wire carrying 1 ampere current on cross-sectional area A is equal to 10 power minus 6 meter square. The electron density of copper is 8.34 into 10 power 28 meter per minus 3. So how can we solve this problem? We know that by the drift velocity of electron, I is equal to current is equal to nqa times Vd. The current I is equal to 1 ampere is given. Q is equal to minus 1.60 into 10 power minus 19 coulombs is the charge of an electron. Rearranging, I is equal to nqa avd. To isolate drift velocity gives Vd is equal to 1 by nqa. By solving this problem, we get the answer Vd is equal to 7 times 10 power minus 6 meter by second. This shows that electrons moving very slowly in this copper wire. So next concepts we will learn in the future are potential difference, EMF and Ohm's law. Stay tuned to this channel MK Trends. Thank you everyone.